In system design interviews, we often have to choose the right database for a given scenario and explain our decision. Databases like MySQL and MongoDB are often considered for read-intensive workloads because of their efficiency and scalability. In this video, let's explore how their unique architectures make this possible. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Imagine browsing products on Amazon, streaming your favorite show on Netflix, or scrolling through Instagram. All these actions involve fetching lots of data in real time. These are classic examples of read intensive applications. But handling such immense read loads in distributed setup is not simple. Let's break down the challenges. Distributed databases face unique challenges when handling read queries. Key issues include latency, consistency, scalability, and index management. Queries across geographically distributed nodes can cause delays. Ensuring up to date data is tricky under high read loads. Scaling indexes and replication strategies requires precision. Optimizing indexes increases storage and operational complexity. So, which databases are the go-to choices for read-intensive applications? Listed here are a few. Now, let's focus on MongoDB and MySQL. What makes them so efficient for read-intensive tasks? You may recall from our earlier video on LSMT that storage engines manage data, search, and data retrieval in a database and are considered the core of a database. Both MySQL and MongoDB use page-oriented storage engines. MySQL uses the InnoDB storage engine, while MongoDB employs Wired Tiger. These engines leverage advanced data structures for optimized reads. Page-oriented storage engines divide data into fixed size pages and manage them within a file or set of files. Each page contains a specific amount of data and can be independently accessed and modified. Pages are typically organized in a hierarchical structure for efficient data retrieval. InnoDB uses B trees for storing data and indexes. Here is how it works. Data is stored in fixed size pages, typically 16 kilobytes. Pages are the smallest unit of I/O between disk and memory. Each page contains keys and pointers organized in a hierarchical B tree structure. B tree is a self-balancing tree data structure used for indexing and data storage. It is designed to optimize operations like search, insert, delete, and range queries by minimizing the number of disk I/O operations. In a B tree, data is stored in nodes. Nodes contain keys which are used for indexing and pointers to child nodes, or in the case of leaf nodes, to the actual data. The keys in a B tree are sorted in a specific order, ensuring efficient search and retrieval operations. The tree is balanced, meaning that the height of the tree is kept relatively constant to ensure optimal performance. Each B tree node or a part of it is stored in a page. Nodes are aligned to fit within the pages. For example, an internal node with multiple keys and pointers might occupy one page. A leaf node containing data records or primary key pointers might occupy another page. The size of a page determines how many keys or pointers can be stored in a single node. Let's understand the B tree structure with an example. Imagine a B tree storing keys 1, 2, 3, 4, 5, and 6. Internal node on page 1 stores key 3 and pointers to two child nodes. Leaf node 1 on page 2 stores keys 1 and 2 and actual data pointers. Leaf node 2 on page 3 stores keys 4, 5 and 6 and actual data pointers. Now, let's see how to locate key 5 in this B tree. Read page 1 to retrieve the root or internal node and follow the pointer to the second child. Read page 3 to retrieve the leaf node to locate the key and its corresponding data. This page-oriented approach allows InnoDB to manage reads and writes efficiently by working on pages rather than individual rows. Let's see how MySQL leverages B-tree for efficient data retrieval and indexing. MySQL's InnoDB uses B-trees for its primary and secondary indexes. The primary index, also called clustered index, stores actual table rows in the leaf nodes, sorted by the primary key. Each entry in a secondary index leaf node point to the primary key values, enabling efficient lookups. For equality queries, the B-tree structure enables logarithmic search time. The ordered nature of a B-trees allows sequential traversal, making range queries efficient. Wired Tiger, the default storage engine for MongoDB, also organizes data in pages. Both indexes and data are stored in pages. Pages are smaller, with default size of 4 kilobytes. The page size is adjustable in MongoDB and is designed for document-oriented workloads. MongoDB does not use traditional B trees for its indexes. Instead, it uses a variant called a B plus tree. A B plus tree is an extension of a B tree. In a B plus tree, the leaf nodes store pointers to the actual data. Internal nodes only store keys and act as pointers to child nodes, optimizing range queries and sequential access. In a B plus tree, the leaf nodes are linked, making range scans more efficient than in a B tree. This structure allows MongoDB to efficiently handle both equality and range-based queries. Linked B plus tree leaf nodes in a MongoDB makes range queries efficient, as data can be scanned sequentially. MongoDB uses the B plus tree structure for both single field indexes and compound indexes. Each index in MongoDB maintains a B plus tree for fast lookup, insertion, and deletion of indexed data. Let's understand the B plus tree structure with an example. Imagine a B plus tree storing keys shown here. The structure would look like this. Internal node on page 1 stores only key 3 and pointers to child nodes. Leaf node 1 on page 2 stores keys 1 and 2 along with pointers to the actual data. Leaf node 1 is linked to leaf node 2 via a next pointer. Leaf node 2 on page 3 stores keys 4, 5 and 6 along with pointers to the actual data. This is the last leaf node and has no further links. Now, let's see how to locate key 5 in this B plus tree. Step 1. Read page 1 to retrieve the internal node. Key 5 is greater than 3. So, follow the pointer to leaf node 2 on page 3. Step 2. Read page 3 to retrieve leaf node 2. Find key 5 in the leaf node along with its corresponding data pointer. For a range query like finding keys between 2 and 5, this is what is done. Start at leaf node 1 on page 2 for key 2. Use the linked leaf nodes to traverse sequentially and read keys 3, 4, 5 in leaf node 1 and leaf node 2. Now that we know the B tree and the B plus tree, let's compare them quickly. MongoDB's B plus tree has linked leaf nodes, which are absent in InnoDB's B tree structure. MongoDB does not cluster data by its primary key the way InnoDB does. The primary index is clustered, meaning the actual table data are physically stored within the leaf nodes of the B tree. In a B tree, pointers to the actual data can reside in both internal nodes and leaf nodes. But in a B plus tree, pointers to the actual data are exclusively located in the leaf nodes. The companies listed here optimize their read-heavy workloads using features like clustering in MySQL or linked leaf nodes in MongoDB. MySQL's structured approach suits traditional relational data, while MongoDB's flexibility excels in document-oriented use cases. Both are powerful tools for read-intensive applications. Understanding these internals will help you choose the right database for your next project. If you found this video helpful, give us a thumbs up and subscribe to our channel for more interesting tech topics. Do check out our other videos on software performance optimization case studies, coding, system design, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time.